So the last property related to intermolecular forces that we're going to talk about is the vapor pressure. So if we look at this diagram here, which should look familiar, you can see that this tells us the fraction of molecules with a certain kinetic energy. So red being higher temperature, you're going to have it be shifted over to the right, so more molecules having higher kinetic energy. And at lower temperatures, shifted to the left where they don't have as much kinetic energy because they're not moving as fast. So this little dashed line here, that would tell us the minimum amount of kinetic energy that a molecule needs to escape from the liquid phase and have enough energy to break all of its intermolecular forces and jump into the gas phase. So you could see, if we look at the blue line, the lower temperature, there's not as many molecules, so that shaded blue area, there's not as many as when we have the red curve at higher temperature. So, and it doesn't matter which temperature you're at, so the lower temperature curve or the higher temperature curve, there's always going to be some fraction of molecules that have enough energy to escape off of the liquid phase and break their intermolecular forces into the gas phase. But as we increase the temperature, that amount will go up. So we're going to have more molecules that can go into the gas phase. And as we do that, as the molecules go from the liquid phase into the gas phase, if we're in a closed container, then those gas molecules are going to exert a pressure. And so as we get more molecules going into the gas phase, we're going to have a higher pressure. So molecules pressure will increase. If we have a closed container, then there's going to be a point where that pressure isn't going to go up anymore if we keep the temperature consistent. So we look at this little picture here. We have a liquid ethanol in the top little vial, and then when we open this stopcock right here, now the vapor, so the molecules go in here into the flask, and they're able to now vaporize. In the flask, so initially it's a vacuum, so there's no pressure. As the molecules vaporize, they're going to start to increase the pressure in the flask. But then at some point, there's going to be molecules that collide back down into the liquid, and they don't have enough energy to escape, so they're going to recondense. So we're going to get this state of equilibrium, or dynamic equilibrium, so kind of moving, where we're going to have molecules vaporizing up into the gas phase at the same rate that gas molecules are condensing back down into the liquid phase. And that's when our pressure is constant. So we have maximized the amount of molecules that can vaporize, and so now pressure isn't going to increase anymore, so that means that some molecules are going to have to go back down into the liquid phase. So this is related to intermolecular forces, because you can imagine that molecules that have a weaker intermolecular force in the liquid phase, they're going to vaporize a lot easier at a certain temperature than something that has higher intermolecular forces. So the boiling point is related to the vapor pressure. It happens to be the temperature at which the vapor pressure equals the atmospheric pressure. Normal boiling point is basically just defined as being when the vapor pressure equals 762 or 1 atmosphere. So normal being 1 atmosphere. So we know that we are below 1 atmosphere since we're higher elevation. We're about, from the lab that we did, I think we're about 0.86 atmospheres, right? So somewhere up here. So that's why our water is going to boil at a lower temperature, because it doesn't take as much to get to our vapor pressure equaling atmospheric pressure. So boiling point, it happens to be a temperature, but it really has to do with the pressure and of the atmosphere as well as the vapor. There is a pretty cool relationship. So this temperature curve here that we've been looking at, we do vapor pressure versus temperature. And you can see that it has like this kind of exponential curve here. So it as it increases, it goes exponentially up. So if you take all of your pressure points here, and it doesn't matter what units, well, they should be atmospheres actually, and you take the natural log of them. So you literally take all your data and you would say, take the natural log of all those data points, and then you take all of your temperature data and you take the inverse. So you do 1 over the temperature, and then you plot those. So now we have natural log of pressure versus 1 over the temperature. Then we get this really cool curve that is a straight line. So it takes this exponential curve and makes it linear. And you can see that the natural log of the pressure versus 1 over the temperature. So that is our, hold on, let me change my color. So we have y as natural log of p, 1 over temperature as x. Then our slope here is negative delta H VAP divided by R. So this is how scientists are able to measure the vaporization enthalpies of different compounds, is by literally just doing this experiment, having a sample, measuring the temperature and pressure, just like you did in the lab, and then plotting it at different points. So we could actually do this with our data that you guys did and find the vaporization heat from that. So let's practice doing some problems. So use a figure to estimate the boiling point of diethyl ether under external pressure of 0.8 atmospheres. So we need to find out what 0.8 atmospheres is in torr. So if we do 0.8 atmospheres, and we know that there's 760 torr in 1 atmosphere, and that's 608 torr. So I'm going to go on here, that's a little bit above this line, and I want to do it for diethyl ether, so that's this red curve here. So we're going to find the temperature. I'm going to have to zoom out a bit, at which the curve, the red curve, the vapor pressure curve, crosses with this pressure. So I'm going to go over to here, go down as good as I can, and we can see that's about, I would say 27 or so degrees Celsius. So that would be the boiling point of diethyl ether if the atmospheric pressure was 0.8 atmospheres. So let's figure out the external pressure if ethanol boils at 60 degrees Celsius. So we're going to take 60, we're going to go straight up, and ethanol is the orange curve. So we can see that this temperature crosses the line right here. So I'm just going to go straight over, and that looks to me about 300 torr. So if we take that, it doesn't ask that, this should be fine, but divide by 760, then we get 0.395 atmospheres. So if you want the temperature of ethanol to boil that low, you have to really decrease the atmospheric pressure. So that's what these curves will look like, is basically going, finding the pressure, drawing a line across, going down to find the temperature that's related to that from where it crosses on the curve, or doing the opposite and having a temperature go up all the way, find where your curve crosses, and find the pressure. There will be some homework questions where you do the Clausius Clapeyron equation, it is extra credit, but I encourage you to practice it. The next thing we're going to talk about is phase diagrams. So this is basically a pressure versus temperature curve, similar to what we saw for the vapor pressure one. But the vapor pressure one's really just doing this red line here, and we're going to extend it into another phase. So here we have, pressure versus temperature. We have all the phases of matter here. So we have solid being at low temperature but high pressure. Then as we increase our temperature, we get to liquid. And then decrease our pressure, we go to gas. So we're basically just seeing what happens as we hold one thing constant, either pressure or temperature, and increase or decrease the other thing. So if we cross this line here, we go from melting to freezing. This line here is vaporization and condensation, and this line here is sublimation and deposition. If we are on the line, we are at an equilibrium between both phases. So actually both phases are happening at once. So the blue line, you're literally in an equilibrium between solid and liquid. The red line, you're in an equilibrium between liquid and gas. And the green line, you're in an equilibrium between solid phase and gas phase. And so they would have properties of both. We have these special points. First one's a triple point. This is the one pressure and temperature point where all three phases, so triple, all three phases exist at once. So pretty cool. And then this critical point up here happens to be the point for a liquid and a gas to now coexist. So basically, if you go to any temperature above that or any pressure above that, so in this little red area, you have kind of like a liquid gas mixture where you don't see either one individually, you see both of them, and it does behave as both. And in class you'll see a video. I'll post a link so you can watch it on your own time as well. So supercritical fluids are gases that liquefy when we have a pressure applied. If we increase the temperature, we cannot compress it back into a liquid. So we won't ever see a meniscus again, which is what you'll see in this video. So that temperature is called the critical temperature, where you can't compress anymore. And that pressure being the critical pressure. So anything beyond is that supercritical fluid. So every molecule will have its own phase diagram depending on its intermolecular forces and stuff like that. So this is the one for carbon dioxide. So you see that at 1 atmosphere, there's no liquid state for CO2, which is why for us, at less than 1 atmosphere, it sublimes. We don't see any kind of liquid phase. It doesn't actually exist in a liquid phase until above 5.1 atmospheres. So we can see triple point is actually a really helpful value because it helps us to know above that pressure, that's where liquid phase can exist. Okay, and the temperature also helps us to know at what temperature it would melt above that pressure. So here's CO2. The next one we're going to look at is water. So notice, you can go back to your other slide, notice for CO2 it kind of goes like that at high pressures. And for water, there's this upward back type of slope. So that's a pretty unusual feature for water. And note there's a really high critical point for water. and that has to do with the strong intermolecular forces. So it takes a lot of a high temperature and high pressure to get it into that supercritical fluid. So let's practice. So here is the phase diagram for methane. So we want to find the approximate temperature and pressure for the critical point. So critical point is number 3. So we can go over and down. Oh, it's better to have a ruler for sure. So let's see. That pressure to me looks like maybe about like 70 atmospheres and maybe negative 80 Celsius. The approximate temperature at the triple point, so we'll go over and down. I would say pressure equals 0.1 atmospheres. And that temperature is, if this is negative 200 right there, oops, 200, then that's about negative 180 degrees Celsius. Is methane a solid, liquid, or gas at 1 atmosphere and 0 Celsius? So 1 atmosphere, 0 Celsius, it's about 0.2. It looks like it is a gas. If solid methane at 1 atmosphere, so we'll take that here, is heated while the pressure is held constant, will it melt or sublime? So we're going to go through and heat. So it looks like it goes from green to blue, so solid to liquid, so it will melt. If methane at 1 atmosphere and 0 degrees Celsius, so 1 atmosphere, 0 degrees Celsius, so up here at 0.2, is compressed, so increased pressure, what state will it be? So we will go up, and it looks like as it is compressed, it will go into a supercritical fluid. So that's kind of what this entails, is starting at a certain pressure and temperature and increasing one of those variables, and kind of going to a certain pressure and temperature and seeing what phase you're at. So based on the phase diagram for methane, what happens to it as it's heated from negative 250 to 0 at a pressure of 0.01, so 10 to the negative 2. So we're going to go from negative 250 right here, oops, right here, up to 0. We can see that it sublimes. It goes from solid to gas, so A. And then use the phase diagram to answer the questions. What's the normal boiling point for methane? So we're going to go to 1 atmosphere for normal, go to where it goes from liquid to gas. So right at that red curve, and we're going to go down. So I would say about negative 150 degrees Celsius is the boiling point at 1 atmosphere. Over what pressure range does the solid methane sublime? So we can see it sublimes from, so this point here, the triple point and below. So anything less than 0.1. So for B, it'll be pressures less than 0.1 atmospheres. We'll have sublimation. And above what temperature does liquid methane not exist? So that's basically saying at what temperature is above the supercritical fluid. So we have our supercritical fluid happening about negative 80. So we'll say up greater than, oops, it's less than, greater than negative 80 degrees Celsius. We have supercritical fluid. Okay, let's put all of this together. So I have CS2 has a melting point of negative 110.8 and a boiling point of 46.3. Its density at 20 is 1.26 grams per milliliter, and it's flammable. So what's the name of this compound? So it is a covalent compound, and CS2 is carbon disulfide. I'm hoping you're trying this on your own before checking the answer. List the intermolecular forces, so we need to do the Lewis structure. So we have carbon has 4 valence electrons, sulfur has 6 each, so 12 total. So we're going to have carbon, sulfur, sulfur, and we have 2, 4, 6, 8 for the double, or for the bond, 10, 12, 14, 16, but we need to have carbon have an octet, so I'm going to get rid of the electrons there and make bonds. This looks like carbon dioxide. So notice it is linear and it's balanced, no lone pairs, so it's a nonpolar, so the only IMFs are LDFs. Write a balance equation for the combustion of it in air. So we have CS2. Now combustion in air is always going to be oxygen making CO2, and instead of water we're going to actually have SO2 gases. So and we can't have water because we don't have any hydrogens. So we're going to balance that. Our carbons are balanced. We need to balance our sulfur, so we have 2 here. Now we have 4 oxygens plus the 2, so 6 oxygens on the right, so we need 3 O2 molecules. So the critical temperature and pressure for CS2 is 512 and 78, so that's where we have that critical point. Compare these values with those for CO2 and discuss the possible origins. So carbon dioxide is at 304 and 73. So pressure, temperature is 73 atmospheres and 304.3 Kelvin. For CS2, we have 78 and 502 Kelvin. Okay, so why do you think CS2 has higher critical point? I'll let you guys think about it. So what's different from carbon disulfide from carbon dioxide? Well, they have a similar shape. They're both nonpolar, so the only difference here is the molar mass. So CS2 has higher molar mass, so it has higher LDFs. So that would explain why it needs a higher temperature. It's kind of like the boiling point, but ish, and a higher pressure to get to that critical temperature pressure. So higher intermolecular forces from LDFs makes it have a higher critical point.